All right, let's see where we are in the proof. We had an interlude of some more definitions and some more lemmas, and now we can get a clear idea of where we are. We actually a long way towards proving this, albeit with one key, the key deepest part still to come. But we've got some hints of what to do there. That deepest part is going to be F being an open map. In other words, roughly speaking, it's locally onto. That it goes in all directions at all points, at least a little ways. Second thing we'd like to know is F is locally one-to-one. That it has to be true if we're going to invert it at all. It's the weakest thing we can imagine for it to be locally invertible. But you know what? I'm going to cross that out because we actually now know we really want to prove and already have proved something stronger, which is that it's locally by Lipschitz. Okay, it's not just true that if 2 points differ, their outputs differ. It's if 2 points differ, their outputs differ by some specific amount. That's the by part in the by Lipschitz. So it's a nice geometric quantitative strengthening of locally one-to-one in particular. And we just you just had it as an exercise in the last part to show that if F is C1 with invertible derivative, then it's locally by Lipschitz. Okay. Now that's going to mean that the G's are defined. Now they're going to be we're not going to have any control over what sets they're defined on unless it's open, but let's assume we can do this. So let's assume that this is going to be true. We're going to postpone that for just another little bit. But if that's true, then this is going to be useful. And in fact, we now know G is going to be locally by Lipschitz as well. That was another exercise that if you can prove this about F, its inverse functions are also going to have the same property. And then in a minute, I'm just going to recap how that was the only really big missing piece in the proof that G was differentiable. That's where we started the real proof of the theorem, is to try to prove this. What we discovered is that we needed some sort of Lipschitz-like condition, in other words, locally Lipschitz on G. But that's true because it comes from that condition on F, and we saw how that came from F being C1 and invertible derivative. Okay, so that's going to be, I'm going to check that off a little prematurely because I'm going to go back and recap it, but we basically have the ingredients for that. G is C1 is actually going to turn out to be easy once we have all this stuff, and I'll do that before we go back to the real deep part of the proof. Okay, so a few videos ago we were doing this main limit calculation. This is where I suggested we jump in, looking at what it would mean for the derivative of G to be A inverse. That's the inverse of the derivative of F at X. And the trick was multiply everything by A, so we can cancel out that A inverse, with a little bit of manipulation, but nothing really deep. We got to here. Notice I've replaced the limit as K goes to 0 with the limit as H goes to 0. That's legal, because we now know that G really is going to be continuous as the inverse of F. We put in our little fudge to replace K with H, just a little algebra. And the thing is, we needed these guys to be bounded. But that's exactly what's provided by G being Lipschitz. So this guy's bounded. This is less than or equal to C, the Lipschitz constant for G. This guy is going to 0. So the whole thing goes to 0. So we wanted to know that this goes to 0. But we've got that A times it goes to 0. And A is an invertible matrix. So this is a limit of vectors in Rn. It's a sequence of vectors in Rn. And when we hit it with this invertible map, that goes to 0. Well, then this must go to 0 as well. Okay, so we've got that G is differentiable. So that's cool. That's a big deal. Alrighty. The only thing remaining now is, remember, we needed F to be an open map for this to have any real meaning, because otherwise this limit wasn't really the kind of limit you can legally take to do a derivative. You've got to make sure that G is defined everywhere near Y. So that's very much something we need. But we're making progress. Okay, so let me just pick off that last thing on the to-do list. G is C1, that its derivative is actually continuous. Okay, so remember, we already know it was essentially that we proved that G is differentiable at all. But once we got it was differentiable, we proved along the way, or we could just get as a corollary of the inverse function theorem, the only thing that actually worked in here was A inverse, which, remember, is the inverse of df of x. Okay, or explicitly, writing everything in terms of y, you take y, let's draw the picture again. It's the thing that confuses a lot of students when they first learn derivatives of inverses, because it's a little subtle. Here's f going here. We want to get the derivative of g, the backwards function at y, and that should have something to do with the derivative of f, the forward function. In particular, it's the inverse of that sucker. But where can we evaluate that? We certainly wouldn't make any sense to evaluate df at y, because f and df are things where the domain is over here. So first we have to take y and turn it back into x by applying g to it. Then we look at df and we take the inverse of that matrix or that linear transformation. So let's just analyze this explicit formula. This is a great example of how easy things are, comparatively easy things are, when you have an explicit formula for something than when you're just trying to show sort of abstract existence and uniqueness, things like that. So this is the composition of three functions. We take y, we stick it into g. Okay, we know that's continuous. In fact, we know rather more about it. It's differentiable and it's Lipschitz. Okay, so if we wanted to make this kind of more hardcore applied math, effective is the word for it, get estimates and everything and really say how bad can this be, that would be a start for that. Hubbard and Hubbard does things like that all the time. Okay, so we take that, y is going into g, that's continuous. The assumption is that df is a continuous function of its argument as a function from points in Rn to matrices. That's f being c1. Okay, so this guy's continuous because we're assuming that f is c1. Now, of course, that's got to come into it because it would be really weird if g is actually better than f. There may be situations where you can prove that, but it'd be really weird. Okay, so it's not surprising that f being c1 comes into it. Then the last thing we do is we take the inverse of a matrix. So that's something that you do need to prove, something that's proved as a homework problem in Schifrin and in some other books. It's in the text in some other books, that the map A goes to A inverse on the set of invertible matrices. Obviously, this doesn't make sense off the invertible matrices, but on the set of invertible matrices, that is a continuous function from the set of square matrices to itself. So it's the composition of three continuous functions. It's continuous. So in other words, g is c1. The operation of taking the derivative of g varies continuously with the argument y. So this is not deep. Really, really not deep. It's just putting things together. It's really following your nose. Doesn't mean it's easy, but it's putting together known facts in a fairly predictable way. So what have we left with? Okay, we're left with that one thing. We need to show, we need f to be an open map. Okay, that's that local surjectivity. For example, so far we could have been analyzing f from, let's say, Rn to Rm, where m is bigger than n, and like maybe it's x1 dot 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 through xn just gets included as the first n coordinates. So like a plane gets mapped in as the xy plane in three-dimensional space. I think everything we've said really would apply to that. This map is amazingly beautiful. It preserves distances exactly. It doesn't shrink them or stretch them. It's an isometric embedding. It's a partial isometry. And so it's certainly by Lipschitz. It doesn't distort distances at all. It's differentiable. All this stuff's good. It's one-to-one. On the image, then there is an inverse function, and on that image, it's really just boring as heck. Okay, so we could have been talking about this all along, but that is not invertible as a map to the big space Rm. Okay, if I take a vector here, I don't have anywhere to send it to, and I'm not even getting close to all those points. So I've got to exclude that. And what's missing here is the openness. The image of this guy is not an open set. The xy plane in R3 is totally not an open set. If I take a dot here, I take a three-dimensional ball around that, it totally pops out of the xy plane. Or another way to say it is that there's no way to vary the input here so that the output varies in these directions outside the xy plane. And so let's be more precise about exactly what we need, remembering that it's a an existence result. And then finally, you might wonder, didn't he start with something about solving equations? So here's what we really need. Given x naught, there is some r greater than 0. Well, let's say I'm going to call it r1 because I'm going to reserve r for something else. Such that for all y in the ball around f of x naught with radius r1, we can solve y equals f of x. Okay, so here's our x naught, and of course we're going to call that y naught. Although for convenience, I might simplify that in a minute. Although I don't know, it's not super essential. So here's f, and I want to know. I don't need to know that everything is hit in Rn here, but I need to know this whole ball is hit. So here's radius r1. Here's some other point y. I need to know that there's some x that hits that. So not caring about one-to-oneness, uniqueness, because we've already dealt with that. We know we don't get it globally, but we've already dealt with the fact that we know we're going to get it uniquely. But we need existence. Okay, but this is where we connect with those methods for solving that we had before. Okay, so that's going to be maybe the last. There's two methods I want to show you, so it'll probably be 2 more videos to complete the discussion of the inverse function theorem.